All right, how's it going, everybody? We are here on Thursday, February 4th. Today we're going to be talking about section 6.8, where we're going to see more on graphs with sine and cosine. Last class, we talked about three of four major properties of sinusoidal graphs, and today we're going to see the fourth property, the one that's kind of the weirder one to discuss. Um, and then we're going to take all four of those properties and use them to do some sinusoidal curve fitting to try and apply these to some more real world scenarios. We saw a little bit of that last class with the modeling the temperature. We're going to do even more problems that are like that today once we have all of our parts here. And I'd like to say, this is one of those times where I feel like I'm like, man, who writes textbooks and puts section titles like this in here? How useful are section titles if you have no idea what it means if you don't know the topic already? I feel like it's a crazy thing. So phase shift and sinusoidal curve fitting just sounds crazy. So I do want to say, like, what are we even talking about here first? So phase shift is the one property that we didn't discuss last video. So we're going to even see how we know even what that means, because we're going to start by summarizing what we saw in the last video. All right. So we talked three properties last class: amplitude, midline, and period. Phase shift is going to be like a fourth out of four properties that we really care to identify when we're graphing trig functions. So we already hit 3 out of 4 last class. And now we're going to get the fourth one today. And we're going to summarize the previous three before we talk about the fourth, to where you're easily going to be able to see, oh, the one that's missing is blank. And we're going to call that thing phase shift. Secondly, sinusoidal curve fitting. What this refers to is the act of attempting to take some data and try to decide what is the best trig function to fit through it. We're going to decide what amplitude is most appropriate, what period is most appropriate, what midline is most appropriate, and what phase shift is most appropriate, to model some scenario, and then to use the equation that we've built to make further predictions about data that we don't know about. So let's talk about these two things. So our first mission for the day is to identify what is phase shift. How do we talk about it algebraically? How do we see it graphically? Once we've got phase shift, then we have all of our properties of our sine and cosine graphs. And so then once we kind of know everything we need to know about sine and cosine graphs, we can use them to apply their concepts to some application problems here. So that's our goal for today. So let's look at what we did last class. In last class, we looked at the graphs of sine and cosine functions. Remember that collectively these are referred to as sinusoidal functions. Every single thing that we're ever stating here is true both for sine and for cosine. I keep on writing them in terms of sine. All this stuff applies to cosine exactly the same. There's no real difference right there. I'm picking one so I have something to write. All right. So the first thing I think that we looked at here was our midline. The midline is sort of the center of our graphs. As they weave up and down, the midline is the one that traverses right through the horizontal center of these graphs. What we ended up realizing is that we could add some positive or negative constant to the end of our trig function on the outside, and that would move where our midline is located. So our midline is located at k. Y equals k. Remember that the midline is a line, right? So we want an equation of a line. It's not like it's a number. The amplitude is just a number. It's a measurement of magnitude. The midline is literally a line that's on the graph, right? We draw it as a dashed line going through the center of our graphs there. And importantly, recognize that moving the midline just takes our entire sinusoidal graph and moves it up or down. So we recognize that this represented a vertical shift. And the last thing I want to say about this before we walk away from this concept here is I know that this is going to do an up-down shifting job, because I can see that our adjustment to the trig function is outside of the parentheses. This plus k affects the outputs from the sine function, and our output variable is the y variable, and that's what controls our vertical motion. So the fact that k is outside the parentheses means it affects our outputs, which means it's a vertical change. The fact that it is addition means it's a shift. The next one that we looked at was our amplitude. Our amplitude gave us the distance from the midline up to the maximum and down to the minimum. In a sense, sort of like a radius, but in only one dimension there, right? A is our amplitude, right? All right, so we get K, we get A, and here we're going to get T for the period right there, like our letters that are describing each of these things right here. And again, you should notice that a is outside of the sine function. Therefore, multiplying by a will affect the outputs from sine. So it affects our y values, not our x values, because it affects our outputs. And here we can see that a is multiplying the sine function, which means it's going to do a stretching job rather than a shifting job. All right, so this is going to be a vertical stretch or a compression. If a was 1/2, then it would squeeze our graph down to only be as half as tall as it used to be. So this is a vertical stretch or compression. Right? A typical sine function has an amplitude of 1. From the midline, we go up to a maximum height of +1, midline of 0, and from our midline of 0, we go down to a minimum value of -1. That's true of both sine and cosine, like unaltered. So if the amplitude is 1, there's no change in amplitude. Amplitudes smaller than 1 are like compressing the graph. Amplitudes larger than 1 are stretching it vertically. The other thing that we looked at was the period of these functions. We know that traditionally sine and cosine have a period of 2 pi radians, but we've seen that we can adjust that. Here we can see that making a modification inside of the sine function should affect our inputs. Our inputs are our x values, and that's how I know that this is making a left-right modification to our graph, not a vertical modification. The modification is being made inside of the parentheses of the sine function, so it's affecting our input values. Inputs are x values, so this is a horizontal adjustment. Just as we saw that this vertical stretch was caused by a multiplication, we also have a multiplication happening here, but it's inside. So it should still be like a stretch or a compression, but it's going to be the horizontal version. Now, one of the things I did last class was I really wrote this guy as like a 2 pi over the period here. I do want to kind of show you a couple quick things right here. Notice that algebraically, I could solve this expression instead for omega. I could multiply both sides. Oh, by the way, this looks like a W. Often people really like using Greek letters in association with trig stuff right there. Technically, that's the letter omega, which looks like the more like swoopedy W that you're seeing right here. I don't care if you write this like a W, call it a W, whatever. I'm going to call it omega because that's technically what it is, but that's I'm not too worried about that. In any event, I'm going to multiply both sides of this equation by omega, and I'm going to divide both sides of this equation by t. And you should see here, the really nice thing about this equation is that it's actually the same thing. You can switch t and omega, and it's still true right there because all you're doing is multiplying one up to the other side and dividing the other one back down in its place right there. So this is kind of what we had written the other day when we looked at our previous video is sine of, I think I wrote it as like 2 pi over over like p for the period. But I'm noticing that our book is using a capital T to represent the period here. Whatever, that's just a name. It's just a letter choice. It doesn't matter. But the point is, this is what we wrote in our last video right there, 2 pi over what the period length was going to be. And so there's several different ways that we can write this right here. But the point is a constant multiplication by a constant inside of our parentheses. That's what's going to do our horizontal stretch or compression, which is what's altering the length of one period, right? One full cycle of the behavior. So my question for you is, what's the adjustment that we haven't described over here? I just scrolled and ruined it for myself. We've seen a vertical shift, a vertical stretch, a horizontal stretch. And so what's the one that's missing is a horizontal shift, right? And that's exactly what our phase shift is going to do for us. It's really just our fourth adjustment. We're going to do vertical shifts, vertical stretches, horizontal shifts, that's the phase shift, and and horizontal stretches. That's our period adjustments right there. Those are really the four main transformations that we need to be able to handle with our trig functions here. So in general, we're going to represent the phase shift as the Greek letter phi. And it looks like a theta, except the stick is going vertically right there. This is and again, this is just one of those things where I guess you can use any letter that you want right there, but it's like, I've like never seen a textbook that doesn't use phi as the letter to represent the phase shift. It's just one of those conventions. It's like why we always use x and y. It's for no reason except for consistency. This is one of those things right there. So the other thing that we learned here is that our shifts are associated with addition or subtraction. just like our stretches are associated with multiplication. So using that intuition, I know that if I want to do a horizontal shift, horizontals, x values, those are inputs. So I want to make an adjustment inside the parentheses of my trig function, which I've done. And it also looks like we want to do addition or subtraction to be associated with a shift rather than multiplication inside the parentheses, which would be associated with a stretch, which is different than a shift, right? A shift is a slide. A stretch is leaving some stuff in the middle right where it is, and the stuff at the extremes gets further away. Right? Now, one of the things that you should recognize that's slightly weird about this equation is the fact that I'm using a minus sign right there rather than a plus sign. And here's the reason why that's a typical thing to do. Remember when we were talking about our period adjustments in the last video, we were saying things like, when we talk about, and I'm going to kind of draw two examples right here. When we talk about sine of 2x right here, I like to use my grocery store analogy. This says you need to leave the grocery store with $120 worth of groceries. The act of applying the sine function is the act of you purchasing the groceries. X is the number of dollars that you need to bring to the store to make the purchase happen, right? This 2 says, well, listen, whatever you bring to the store, X, it's going to get doubled before you buy the groceries. You're going to do 2 times X, then apply the sine function. So that means to me, I could get away with only contributing half as much. So notice here, this doesn't make us twice as wide. This made us half as wide. You only have to contribute $60 and you can buy $120 worth of groceries because somebody standing outside the grocery store is going to multiply your money by 2 before the purchase is made. So it sort of has that inverse effect as to what you're expecting there. Very, very similarly, if I were to do something like sine of x minus 2, just like this looks right there, our question is, what impact does this have? Which direction does this shift us here? All right, that was our conclusion there. Well, this is like saying you're going to bring X dollars to the grocery store, and it seems like what's going to happen. All right, now we're back in Humboldt County. It looks like somebody's going to take $2 away from you when you walk into the grocery store, but you still need to bring home $120 worth of groceries. So now the question is, how many dollars do you really need to bring to the grocery store knowing that somebody's going to steal $2 from you? Well, it looks like now you need to bring $122 to the grocery store because somebody's going to take 2 from you before you get to make your purchase. So it seems to me that by introducing a minus 2, that actually means that our x values need to get larger to compensate for the 2 that's going to get taken away. And so where we used to be able to plug in, for example, x equals 120 to buy $120 worth of groceries, we now need to plug in x equals 122 to receive that same benefit of $120 worth of groceries. So what this is going to do is this is going to shift us to the right by 2, not to the left by 2, which is certainly what your intuition should tell you. Whenever you see minus things, you should think getting smaller going to the left. But what I'm really thinking is because $2 are going to get taken away from you, you need to bring $2 more to the grocery store. And that word more is our right shift right there. All right. So this is shift right by 2. So the kind of thing that you got to see is happening here is that, like, when we did our midline stuff, we just added k and we went up k. We subtracted k and we went down k. That followed your intuition perfectly, and that's because those were results that happened after the sine function had already been applied. When we make modifications before the sine function's been applied, like these multiplications by 2 and subtractions by 2, they're going to end up having sort of an inverse effect as to what you would expect. The most common mistake for students to make with sine of 2x is to assume that our graph is now twice as wide. But if you really think about it, you only have to contribute half as much x because it's going to get doubled for you to get the same result. So our graph is actually half as wide. It's the opposite of what your intuition says. Similarly, when you think of subtracting 2, you think going to the left. But really what's happening here is because you need to contribute enough x to essentially achieve the same result, you need to contribute 2 more than you used to have to contribute. So that's going to shift our entire graph to the right by 2, not to the left by 2. So broadly speaking, whether you've taken algebra before or not and discussed all of your transformations, a thing that I like to remember is my transformations that occur outside of the function, like adding k and multiplying by a, those perfectly match my intuition. Adding k makes us go up k units. Subtracting k makes us go down k units. Multiplying by a of 6 makes us 6 times as wide. Multiplying by a that's 1/3 makes us only 1/3 as tall. Perfectly matches my intuition because these are output adjustments. when we perform input adjustments, those are always going to have the opposite impact as what your intuition suggests. By multiplying by 2, it actually made us half as wide, not twice as wide. By subtracting 2, it actually moved us to the right by 2 instead of to the left by 2. And the reason is because our x values have to compensate for the action that's happening by that constant multiple. So they're sort of undoing it. A multiplication by 2 means you get away with half as much x. So it's undoing it. So it's a sort of our opposite of our intuition here. So that's kind of how I keep track of how my 4 different transformations here all work. Output adjustments perfectly match your intuition. Input adjustments are exactly the opposite of your intuition. Multiplying by large numbers makes you narrow. Subtraction moves you to the right. Addition moves you to the left. Right? Opposite of our intuition with those statements. Now, unfortunately, the phase shift has one little extra bugger that goes along with it that we need to be able to figure out here. And what I want to do is go to Desmos and look at this guy right here. All right. So I'm going to say there is an algebraic technicality that we need to be careful with the phase shift. It's the reason that the phase shift stuff got parted out into its own section in the textbook, separated from the other 3. The other 3 are pretty easy to deal with right here. Period is a little bit weird, but it's so important. Phase shift is, it's not hard to deal with, but like it's easy to make a small mistake, and we want to see where that mistake is going to happen. So what I want to do is I want to go to Desmos and I want to graph these 2 functions and compare what happens as phi changes. And very importantly, the big thing to notice that's the difference between these 2 is that this has a 3 in front of the x before we do the phase shift, and this is just a straight up phase shift with nothing else. So let's go to Desmos and see sort of the comparison between these 2 guys and see if we can figure out why this one doesn't quite work out exactly like we think that it does, and think about what slight adjustment we should make to how it looks so that we know what's actually happening here. So I'm going to pop over into Desmos. Yay. And I want to graph first my simple one right here. So I'm going to graph y equals the sine of x. And I'm going to do minus. Remember, that's typically written with a minus there. And check it out. In Desmos, you could literally type phi. P, H, and when I type the I, it just automatically turns it into phi because this is like a common variable to use. So Desmos is familiar with this. I'm going to click to add a slider for phi. And one of my only beefs with this in Desmos is it always starts that variable at 1. I want it to be starting at 0 right here. So I'm going to just slide this over to 0. And so this is saying how much phase shifting are we doing? And the answer is none. We're not shifting at all right now. We have a shift amount of 0. I'm going to increase phi, and what we're watching is as I make phi bigger, our graph is just shifting to the right. Every little bit that we move it, it shifts to the right. Notice that our, let's see here, if I come back here, let's kind of follow a point along right here. This point where we hit the x-axis right there is at 0, 0, and watch that if I shift by, for example, 2, then that point is now located at 2, 0, right? We have shifted to the right, not to the left by 2. This is the equation sine of x minus 2, but it actually shifted us to the right by 2 units right here, all right? And I think one thing that'll be a little bit helpful for me right here is let's go ahead and throw a point on this graph. Desmos can graph points for us as well. I'm picturing that I want to follow this point right there. I want Desmos to put like a permanent point on this. But what I mean is like when I move this graph, I want that point to move with it also. So I'm just going to make the point's location to be what I know that it should be. Notice that this point is always going to have a height of 0, always. And what's its width going to be? Well, right now the x value is 0. Notice that when I shift to the right by 2, the x value is 2. It looks like that point just has coordinates of phi 0, right? So let's go ahead and put that point on there, and you can see it just showed up as a dot right there. And the nice thing now is that now as I slide this graph, you can see a point remaining in place. So it kind of helps us to see the action a little bit better, right? No shift, it's centered at the origin. Shift by 2, it's centered at 2. All that kind of good stuff right there, right? So now here's what I want to do. Now that we've seen that this phi does do the phase shift, the shift horizontal the way that we expect, shift left with, actually, sorry, let me say one other quick thing. Here, phi is -3, so this is actually sine of x minus -3. This is the function sine of x plus 3. That plus 3 is shifting us to the left by 3 units again. Opposite of your intuition. I expect you to think that plus 3 moves us to the right. But because we're compensating, we get to contribute 3 fewer than we used to have to contribute because it's plus 3. 3 is going to get added for us. So we can get away with 3 fewer of our contribution. That fewer, that lesser, that's us going to the left. All right. So now here's what we should do. Let's go ahead and change this function to now be sine of 3x. So we know what to expect here. This 3 is going to be a constant multiple of x. Therefore, it should be a stretch or compression. We remember that input alterations should be the opposite of our intuition. So multiplying by 3 is not going to make us 3 times wider. It's going to make us 1/3 as wide. So what I'm expecting to see here is rather than a period of 2 pi, I'm going to experience a period of 2 pi divided by 3. It's only 1/3 as wide for our period here. All right, now watch this. So I want to very importantly go back to recenter this guy here at 0, 0 before I make my adjustment. So one thing you should notice here is we're currently at pi halves. I think that that point should only be 1/3 as far away from the y-axis in a second. So I think it should be at pi sixths as soon as I type a 3 right here. Let's see if that happens. Yeah, our first peak is at pi sixths now instead. 1/3 of pi halves. But here is the weird part. I still want this green dot right here. And by the way, I'm noticing that I'm using green and red right now. Maybe now is a good time for me to get away from colors that are potentially more difficult for us to see. Whatever. I think that'll be fine right there, purple and green. Actually, isn't it? I believe that I'm supposed to be using blue and orange for colorblind goodness right there. I've been told. Again, if you guys ever have problems seeing my stuff, let me know what colors are better for you. Some of these things might be easier, harder to see for other people if you're watching the video later. I don't know. If these are ever hard to see, just let me know. So I've got my point right here, and what I want to do now is I want to slide this and watch the dissatisfying thing that's about to happen. Uh-oh. Our point isn't on the graph anymore. It's not sticking to that same spot, right? I wanted this orange dot to be representative of our first crossing of the x-axis of the origin, potentially shifted, but it doesn't seem like it's moving with the graph anymore the way that it was a second ago, right? When I didn't have the 3, the dot stayed at that intersection location. But when I introduced this 3, it now seems like our point is not any longer representative of that intersection location. Here's a thing that I might do for myself. Maybe I want to go out to phi being equal to 6. Oh, by the way, I guess there we go. Now, what I kind of want to watch here is this. I'm gonna go back to 6 again in a second, but the problem is that my dot's not doing my guiding job anymore. So now your eyes have to do the guiding job. So your job right now is, as I move this graph, we know that the orange dot isn't doing its job anymore. Your job is to watch this point of intersection right here that's currently at 0, 0. Watch where it goes to as I take phi to 6. Your job, don't look at the orange dot. Look at that point of intersection right here on the blue curve right there. Watch it move. So here I am at phi equals 6. And if you were watching, that point before has now moved only 2 units. It didn't move 6 units when we shifted it with a phi being equal to 6. It only shifted our graph 2. Why did it do that? All right. I was expecting to see a phase shift of 6 since phi was 6, but it seems like we only shifted our graph by 2 units, and it seems like that 3 has something to do with it right there. All right. So let's come back into Microsoft Word and do a ever so slight bit of algebra right here to see why this is working out right like this. All right. So back in Microsoft Word, what we just saw was when we did y equals sine of 3x minus 6 only shifted right by 2. Not by 6. Why was that the case? Well, it turns out, and here's our little algebraic technicality that we're talking about here. I don't ever want to write a phase shift in this format if there's that constant multiple of 3 hanging out right there, or any other constant multiple affecting the width of our period there. Right? What we have to do to write this in a way that's actually going to be interpretable to us is to factor out this 3 on the inside. 3x minus 6, there's a common factor of 3 amongst both. I can factor it out to write this as 3x minus 2 on the inside. And now this is going to look to me like my sine of omega times x minus phi, according to those terms that we had before. Now this 2 is my shift right by 2 that we were seeing there, right? So shift right by 2 is handled by this term right here. But the key is, and here's our technicality for this, you can't just look at the number that was added or subtracted on the inside and say, that's how much we shifted by. It's not necessarily. Unless we have this factored out to where we're only modifying x, not modifying something like 3x with our subtraction by 6, this is when it's truly representative of the amount of shift that we're actually experiencing. So what this is saying to us is that we don't really want to write stuff like this. We do want to write stuff like this when we're discussing our phase shift, because now phi is truly a like number of units left or right that we shift, whereas here it's not. Here we're actually shifting by phi divided by omega units, and that's hard to read. So this is just to say it's easy for you to slightly trick yourself into your interpretation of an equation that has a phase shift, or writing an equation when you have a graph that has some phase shift in it. It's easy for you to sort of, like I'm saying, kind of accidentally trick yourself, because this seems perfectly good. You've got your multiplier that's going to affect your period. You've got your addition subtraction that's going to affect your shift, your phase shift left right. It's got to be factored out from your period modification term right there for us to actually be able to say phi is the amount of shift right there, right? And so we don't, in general, just you shouldn't do this to yourself, because now you've got to do some sort of mental math. It's hard for you to make guesses. It's often the case that our omega term is fractions involving pi, so then to do phi divided by omega is really like a bad idea right there. So the point is, don't leave your equations in that form. It's sort of it's just one of those things that's just going to make it harder for you to understand, or harder for you to communicate to somebody else what you mean. So in practice, it's a pretty good idea to have these, to have that omega as a factored out quantity right there. It's much, much better for us. So what we've now got all together is, we know that constant multiples of A are going to stretch us. That's our amplitude term. We know that positive or negative, that our addition or subtraction of K is going to vertically shift us up or shift us down. We know that constant multiples of omega are going to stretch or compress us horizontally to change our period. And we know that phi is going to handle our phase shift, our left and right shifts. And one other thing I want to say before I walk away from this equation right here is A straight up is the amplitude. K straight up is the midline. Phi straight up is the phase shift, as long as you appropriately have a factored expression in there and not a multiplied out expression. The only one to also kind of watch out for is omega isn't just the period. If you put a 2 there, the period isn't 2. The period is half as much as it used to be, so then it's pi. So just remember, for omega, you always still have a little bit of algebra left to do right there. So where we can say omega is 2 pi over the period, right? So you still have a little computation for omega right there. But the other ones, they just are the value that they look like they are. And notice, it might be the case that you just want to write your generic equation just like this right there. Just write it as 2 pi over t, where t actually straight up is the period. Right? So this is our like fully descriptive sinusoidal function. Remember, by the way, cosine could also be in there as well. And so what I want to do is, let's go to Desmos and look at this guy right here for a minute. You want to play with slider bars in Desmos. I am serious that this is like a. I mean, I don't think any of you are looking at this right now being like, oh yeah, that equation's easy. I got that. It's not. There's a bunch of parts that are kind of complicated here. Let Desmos do the heavy lifting for you in terms of thinking about each of these things. I want to type exactly this into Desmos and feel the immense satisfaction of having 4 slider bars to control all of the features of my graph. All right. So let's go over to Desmos and watch that happen here. So I want to graph the most general sinusoidal I can. Capital A, cosine. I'm going to do my version of 2 pi over t, so that t is just straight up what the period is. X minus phi plus k. Desmos is going to offer me the opportunity to add a slider for all those things right there, which I want to do. Now let's move some things around. What I want to do first is just straight up graph the baseline cosine function. So that means my amplitude should be 1. We normally just have a constant multiple of 1. My t here, let's do some things. Let's at least get rid of our phase shift. And let's get rid of our midline shift. And I at least think that I want these t's to be in terms of pi. So let's maybe make them like, I don't know, like a step size of pi fourths or something like that. Um, okay, I don't really think we need to do that. Maybe let's just do this. What our normal period is 2 pi, right? So there we go. This is the graph of y equals cosine x. And let me just do this real quick. Why would it give me 2 black graphs back to back? What's wrong with you, Desmos? Help me out here. There we go, red. And so now you can see, if you can see red here, then you can see that this cosine graph, the plane cosine graph, is clearly laying directly on top of this graph right here. So it looks like this graph, as we currently have it. Oh wait, where'd my slider bar go for t? I still want to. Can't I like do? Oh man, are you kidding me here? Add a slider, right? Okay, I'm going to do the stupid version of this and take this out to like there, 6.3. It should be 6.28. That's really, really, really close to 2 pi right there. Yeah, we can't even see any difference right there. 6.3, really close to 2 pi. So the nice thing that we can do now is you can now say things, okay, I want my amplitude to be 5. I want the top to go up to positive 5 and the bottom to go down to negative 5. Well, let's just stretch it till the amplitude's 5. Okay, now maybe, I'm going to zoom out a little bit. Now maybe I want to shift it up so it actually goes from 0 to 10 instead of from negative 5 to 5. Maybe I want to shift it up by 5. Well, we can take our k value and just make it positive 5 and shift it up by 5 right there. And oh, what do you know? We're now sitting between 0 and 10 instead. Maybe you say to yourself, I want to shift this guy to the right by 2 units. Well, I can take my phi term now and I can shift. And by the way, notice that our top right now is at, okay, our top right now is at 0, 10. I can shift it to the right by 2 units and it is now located at 210. We shifted it to the right by 2 units. You can change your period. Instead of having a period of 2 pi, maybe you want to have a period of like 4. I don't know. And now with this period of 4, watch what we can see. It's, oh, what do you know? There's 4 units from peak to peak right there. I can see that period going from 2 to 6, from peak to peak, right where we go ahead and do our repeat again, another loop that's out there, right? So this graph right here, I think, is a really, really, really useful thing for us to be able to play around with. This is you giving, you have the control now. You now have 4 levers that you can do to maneuver to literally produce any single sine or cosine graph that there could ever be, right? It's really, really practical. I think that you should use this to help you with all the graphing things that you do. So I am going to, what I'm going to do is, by the way, notice if you ever have a graph that you want to share with me, you can click the share graph button on Desmos right here, and it will just make a link that's like literally exactly all your specific stuff right there. So I'm just going to click copy right there, and it's copied the link. And now I'm going to go pop back over to Microsoft Word here, and I am just going to say in here, now let's go ahead and just going to put that link right there. There we go. Now that link's there, you guys can grab that if you would like. It's got all that good stuff in there. It's got this graph particular. And I like it with a 2 pi over t because then literally t is the amplitude rather than something where you still have to do a little bit of math. Or sorry, t is literally the period rather than like one computation away from a period. Nice. So let's look at some examples here. From this general form, right, these general forms that we've got right here, let's identify the four features associated with each of these two example functions right here. Right? So 2 sine of 3 times x plus 4 and negative 6 times cosine of pi x minus 2 plus 3. What I want to know are, what are these four things? What's my amplitude? What's my midline? What's my phase shift? What's my period? Right, that kind of good stuff. It looks to me like our amplitude is an easy one for us to always grab. Our amplitude in this case is 2, right? This is going to be twice as tall vertically as it normally would be. It's stretched by a vertical factor of 2. Our midline is asking the question, what line goes horizontally through the dead center of our function? And notice here, the midline is normally held with this plus k on the end. Well, really, it's like there's a plus 0 out there. So this is going to tell me exactly where my midline is right here. That's my y equals 0. Remember that the midline's a line. I'm literally giving the equation of a line for the midline as opposed to just a number. It's a line. It's a whole equation. It's not just one number. What else do we want to see here? What is our period? Well, notice here that we were just given the number 3 as a coefficient in the thing that it's in the term where we adjust our period. What we know is that 2 pi divided by the actual period is that number 3 right there. So I could say, I'm gonna scroll up here and say a different thing. Here, what we said was our period t is 2 pi divided by omega. Our omega is 3, so it seems like we're going to get t equals 2 pi over omega, which in our case is 2 pi thirds. That means that one period is only 1/3 as wide as it used to be. It used to be 2 pi wide. Now it's 2 pi over 3 wide before we start repeating our behavior again. This has compressed us by a factor of 3. And finally, what is our phase shift? And one of the things that's really important about phase shift is that I really want to know a direction also that's associated with this thing. Remember that we experience the opposite of what our intuition tells us. When you see +4, I absolutely expect that in your mind you think that +4 moves us to the right, and so you need to remember that it's the opposite of our intuition, and this will in fact move us to the left by 4. The reason is because since when you go to the grocery store, somebody's going to hand you $4 when you walk in the door, meaning you can get away with bringing 4 fewer dollars than you used to have to the grocery store and still buy the same amount of groceries. That 4 fewer is that shift left, right? So this is a left by 4. Okay. So let's go take a peek in Desmos and see if this agrees with what we just said right there. All right, we were just looking at, and I'm just going to use this. I'm going to bring everything back to where our starting spot right here. 6.28, more like what I'm looking for there. Amplitude of 1 is our base case. You can see this reconverging on the original cosine graph here. Phase shift, we normally have none. Midline adjustment, we normally have none. So here is our cosine function, although I'm recognizing that we're actually looking at a sine function back in Microsoft Word right here, a sine function, so I'll just change my function in Desmos. Okay, so there we go. So our sine function, it passes through the origin, increasing through the origin. We were looking for, so what were our features here? So an amplitude of 2. Trying to grab the wrong screen. An amplitude of 2. So we're twice as tall. A midline of y equals 0. That just says keep not adjusting the midline. We already had a midline of 0. That's the baseline default. That says keep not adjusting that. Period. We want a period of 2 pi thirds right there. So this is a case where it's actually probably, well, I don't know. I can just ask Desmos real quick. What is 2 pi thirds? About 2.1. So I'm going to go to my period here and make it about 2.1. I guess I could have done that mental math in my head. By the way, notice that that means that all I was really doing is taking 6.3 divided by 3 because we're 1/3 as wide for our period. 6.3 divided by 3 is 2.1. And then again, these are just my like quick rounding versions of some fractions of pi out there. So here our period is only 1/3 as wide. And so now we can see we go about 2.1 is our gap between x values right there instead of the 6.28, about 2 pi. And our final adjustment that we were making out there was our phase shift said shift left by 4 by by making some positive amount of phi out there, right? Oh, I'm noticing, by the way, my graph is shifting to the right, not what I wanted. I wanted to shift to the left. I'm noticing that I built that minus sign into the equation to handle that for me. Notice that when my phi's are negative, x minus a negative is actually that plus 4 that we wanted to be doing right there. So there's our graph shifted to the left by 4. So this is apparently the graph of interest that we were just looking at right there. And by the way, I think I can just, what was it now? We had a 2 sine of 3 times x plus 4. And let's do it over here. 2 sine of 3x plus 4. And oh, what do you know? It's laying right on top of it right there. So we can verify this by graphing them both in Desmos and then seeing that the adjustments that we made here were exactly the same as the ones that we made here. When I say exactly the same, almost. That's a decimal approximation for 2 pi over 3 right there. It's close enough that we can't quite see a difference in our graphs right there. But we should feel good about those adjustments that we just identified. Cool. Let's do another one here. If we look at y equals -6 cosine of pi x minus 2 plus 3. Okay. So what do we got right here? Well, I think we should identify, let's just identify these in the same order, right? Now, one of the things I want to talk about here is that our amplitude here, I always think of this as, and I think the book even says that this is really the absolute value of -6 right here. The amplitude is really just 6. And again, you should think of amplitude as like the radius of a circle. Just because radius sometimes points this way and sometimes points this way, you don't call this like the negative radius and this the positive radius of a circle. It's just a distance that's being measured. The distance from the midline to the top or the distance from the midline to the bottom, either one of those, it's just a distance, so it's a positive value. I do want to identify what is this negative telling me right here. So I'm going to say negative. I'm going to say amplitude is always positive. So here's the way that I think about this. In my mind, that negative is very much attached to the cosine function, right? If that 6 were gone, it would just be the negative cosine of something. I like to think to myself that there is the positive cosine function that has a maximum at 0, right? Gets to its maximum at 0. Therefore, the negative cosine function, since that negative is on the outside, it should affect our outputs, our y values, and it should flip our y values. The y values that were positive are now negative, and the negatives are now positive. So that means to me I should be expecting to see a graph that's going to do that kind of stuff around the x-axis right there. So I'm picturing these being modifications of the negative cosine of x function. And I'm thinking of that cos x function as being different than the negative cos x function, even though they're really the same. That's also just another one of our transformations there, the vertical flip, right, or reflection. But again, negative amplitude is always a positive number forever. There's never a negative amplitude. It's always the absolute value of that value out there. That negative says to me, change the shape of the graph that you're modifying by flipping it. So amplitude is 6. What else do we got here? We got our midline. Well, it looks like this graph should be centered at y equals 3. That's the line through which it's going to be doing its wobbling at the center there. What's the period of this graph? Well, this one's actually going to work out a little bit nicer. It's going to be 2 pi over the 2 that we see. Or sorry, no, it's going to be actually even better than that. It's going to be 2 pi over pi, the coefficient sitting in front of the x stuff right there. So the period here is just 2. This should be exactly 2 units from peak to peak from valley to valley, from mid to mid, something like that, anywhere we start repeating the process again. Now, the trick question here, and man, there's no such thing really as trick questions, but if there ever was, it's this one right here, the phase shift. The very important thing is that it is not right by 2. Really, we should be thinking of this as factoring out that pi, right? Now, factoring is a division process, just like you would redistribute it if it was being multiplied back through. So I'm dividing pi out of each term in here and pulling that pi to the outside. Pi times x divided by pi is just x. 2 divided by pi, well, I don't know, that's just 2 divided by pi, right? So there is my factored form inside of that cosine function there. I have factored out a multiple of pi. 2 over pi, really gross number, don't care, it's our answer here. Notice that since it is a minus, our opposite of our intuition says that pushes us to the right, not to the left here. So this should be right by 2 over pi. So anytime you're talking phase shift, remember, you don't want to be in the multiplied out format on the inside. You want to be in the factored out format on the inside so that you are literally just reading off how much your phase shift is rather than having to do the little bit of math, right? So whenever I see equations that look like this, my first move is to just rewrite the equation with a factored thing inside of the cosine or sine function right there. Then I can directly interpret all of my components here. So let's again pop back over to Desmos and see it, and then we will draw some graphs and then look at our application problems for the day. So back over in Desmos here, I'm seeing that we wanted to do an amplitude of, now, in this case right here, I am going to include the negative along with my amplitude term only because the slider bars make that convenient for me. And by the way, also notice an amplitude of 0. Well, no kidding, an amplitude of 0 is a flat line. That means don't go up or down from the midline. Right? That's zeroed out all of our actual action there. So here's my amplitude of negative, we got to go all the way to negative 6 for our amplitude here. What else? What other features did we have? We had a midline of y equals 3. So I'm going to shift this guy up by 3 units. There we go. We've shifted up by 3. You should now see that this graph is going from 9 as a maximum to negative 3 as a minimum because 3 plus 6 gave us 9 and 3 minus 6 gave us negative 3, right? So we can tell what the max and the min are right there. We also had for our features here that our period should just be straight up 2. Not any pi stuff was involved right there. So I'm going to take my t term and just make it, it almost was right there, right? Period is just 2. And then as our final thing right here, our phase shift should be 2 divided by pi. So I'm just going to go here and maybe just type in 2 over pi as the phase shift. And it's shifted us by that 0.6366, whatever it's going to be right there. If you define phi to be 2 over pi, it'll plug it into that guy right there. And so here we go. We can see our final product right here. Got some kind of weird numbers for like our maxes up there, but look at them. The x values from peak to peak are exactly 2 apart from each other. So it looks like our period of 2 was acknowledged here, exactly as we wanted it. We've got that period of 2 going on right there. It seems like we have shifted by some amount relative to where we started right here. Notice this 0.637. It used to be that the negative cosine graph achieved its minimum at x equals 0. Now it achieves its minimum 0.63669 units to the right of that. And that's exactly where we are right there. That number right there is that x value right there because we shifted this point to the right by exactly this many units. This used to be right on the y-axis, and now it's a little bit off of the y-axis because it was our phase shift. It shifted us a little bit off to the right there. Right? This graph has all those features that we were able to sort of verbally identify there. Cool. We'll come back to Desmos some more here today, don't worry. Let's see if we can graph some of these guys by hand now that we kind of know all of our parts here. So hopefully these will go kind of a little bit faster right here. So let's do some by hand graphing here. First one, y equals negative cosine of 4x. I got to think about a couple things. What does the negative cosine function look like? And what does the 4x do for me right here? 4x says 1/4 as wide. or 1/4 the period. So my new period then, it's 1/4 of 2 pi, which should be pi halves. And we can get that here by saying that omega equals 4 tells me that our period is 2 pi over omega always. 2 pi over 4, and we're going to get pi halves. So that says my new period is pi halves. That's one adjustment that we're making relative to the original cosine graph. The other thing that we got to do is we got to think to ourselves, what's this negative doing to us, right? So we know that our y equals cosine of x graph. Well, when we graph this guy, and I did this one just a minute ago, I know that cosine of 0 degrees or 0 radians, cosine measures width. So we have all the width. It's a positive 1 is what we get. So at 0, we get to that height of 1 right there, right? I mean, honestly, that's helpful for me. I'm not even graphing the function. I'm just saying, yeah, cosine's the one that starts at the top. That's all I really remember here, right? It should be doing stuff like this, right? Well, that means to me that if we're going to look at the negative cosine function, that says take all of your outputs from cosine, your y values, and make them negative. So positives become negative, but if you apply a negative to negatives, they become positive. So this should result in like a vertical flipping out there, right? So this should now be something like this, to where we go through at the minimum instead of at the maximum right here. It looks like our amplitude is still 1. It looks like our midline is still y equals 0. It looks like our period, we now know, is pi over 2. And it looks like our phase shift, there is none. Phi, okay. Can't draw phi, gotta draw theta. And importantly, our function is the negative cosine function, right? I really think of there being like 4. Sine and cosine, negative cosine. That's kind of a more helpful way, in my opinion, to think about this. So here's what I know. The midline is going to be at y equals 0. My amplitude is 1, so I'm going to go all the way out to positive 1 and negative 1. I know that the negative cosine function reaches a minimum down here at negative 1, so I know that that's a point on my graph. And the next thing that I know is that this graph, it should really only take pi halves to experience an entire full cycle. So I'm thinking from down here, it's got to go all the way up and all the way down again by the time we get to pi halves, which is right there. So what I think a thing I can do for myself is basically just say every pi halves, I know that I'm getting back down to the minimum again. Right? Boom. There's a bunch of points that must be on my graph. I know that negative cosine has a minimum of negative 1 at x equals 0. And I know that this function will repeat itself every pi halves. Only 1/4 as wide as a typical cosine function. It's been compressed by a factor of 4. The other thing I know is that all of my points in between, my maximum points, they're going to have to be occurring halfway in between, right? Halfway in between 0 and pi halves should be my pi fourths that are going to be right here. And so I think I can go ahead and place all my maximums that are also, so this is at x equals pi fourths. Notice that this one, that's at 2 pi thirds and 5 pi sixths, so that's 3 pi fourths. That's halfway between. What's the difference between 3 pi fourths and 1 pi fourth? Is 2 pi fourths. 2 pi fourths as a fraction reduces down to pi over 2, right? So we're getting that repetition happening there as we expected. Finally, I'm seeing things like if I were to plug in, well, actually, let's see here. I don't think I can quite make that call right there. I was about to say something about pi 6 or pi thirds. I do think I can see where does this hit the x-axis. When does cosine get out a value of 0? I know that occurs at pi halves, right? Cosine of x hits the x-axis at pi halves. Because when we're at pi halves radians, we have only vertical stuff, so no horizontal stuff, so cosine is 0, right? So therefore, it should be the case that cosine of 4x says my input's going to get multiplied by 4 for me, so I only need to contribute 1/4 as much as I used to have to contribute to get the same results. So I only want 1/4 of that. So it seems like pi eighths is where we're hitting this thing. So that's actually going to be a little bit before that pi sixths guy right there, right? Smaller than pi six. It's going to be pi eighths. So just to get a little bit clearer description of what's happening right there. Oh man, I really set myself up for a tough one to draw here, didn't I? And so when I ask you to graph a couple of these by hand, I'm not going to go too crazy, but one of the important things that you are going to have to do is you are going to have to do a very clear job of labeling lots of axis values because otherwise I have no way of telling if you actually drew the graph right. Okay, so things like on these graph guys, when I do ask you to graph these things, like on the homework, I'm going to ask you to identify things like where is the first positive x value at which this graph hits the x-axis? You're going to tell me pi eighths. I'm going to ask you where is the first minimum and the first maximum that this graph occurs? State the amplitude, midline, period, phase shift, and what function you're graphing. Like stuff like that. Good descriptors out there since kind of all these trig graphs, like you could just wobble your paper up and down an axis and be like, that's the graph. You just got to number the axis carefully and it's right. That's not, obviously a good way to go about doing these right here. So we want to identify the features, use the features to graph a good looking graph right there. So there's my negative cosine of 4x, right? And again, positive cosine starts at the top, therefore negative cosine starts at the bottom. Sine starts in the middle, right? It passes right through at the center right there. We'll see that in a second. So, we should graph this in Desmos and verify some of these things. Negative cosine of 4x. Negative cosine of 4x, we go in and we look and we say, hey, Desmos, what's going on? Well, we can see that it's getting to the bottom at -1 just like we thought. Sorry, I got to slide over. Here we go. Desmos, graph for me negative cosine of 4x. Just like we thought, we're getting to a minimum down here at -1. Our maximum is going to occur just like we said at pi fourths. Hang on, I'm going to pop back over. Yeah, x equals pi fourths. It's right when we said that we were getting to that maximum of 1. We also, I think the other very important thing here is we identified that pi eighths, I want to draw this on this guy right here. This kind of matters to me. X equals pi eighths is exactly that location at which we determined we hit the x-axis. And if I come back over to Desmos over here, I'm going to say, hey, where do we hit the x-axis at? Oh, right at pi eighths right there. So it looks like we nailed it for this guy. As we know, everything just repeats from then on. We're just going to get more of the ups and downs out there. So I think we identified the key parts, found some key locations on that graph. That was good. So let's do another one here. 5 sine of x plus 3. A little bit faster here. I can see things like our amplitude is going to be 5. I can see that our midline is y equals 3. So what I want to do a little bit more carefully here is it actually, like the last graph, we didn't do any like vertical adjustments. It was only, well, we did, but it was a reflection. So in this case right here, it looks like our midline is y equals 3. It's right there. I know that my amplitude says we're going to go up 5 and we're going to go down 5, right? So I want to go down 5 from 3. That's down to -2. I know that -2 is the lowest value I can ever get out from this function. I can also go up 5, up to 8. So I know this is my midline, my max line, and my min line out there. Everything's going to be stuck in between the top and bottom curve, and the middle curve is the center that it will pass through right there. The only other thing I have here is just the sine function, right? I don't have the other types of modifications here. I know that the positive sine function, sine of 0, asks what's the height on the unit circle at 0, and the height is 0. We haven't gone up or down at all. So I know that sine of x goes through the origin. I know that as theta increases, we're gaining positive height. So positive theta, positive height, that says we do go off in this direction. So when I think about my sine graph, that's all I really think about in my head right here. But I do know that it's going to be doing our stuff that looks like this, right? Conversely, if it was the case that we were looking at the negative sine of x graph, it seems like we'd again just be doing a vertical flip. Sine of 0 is still 0 because it's sine of negative 0 now, but now it seems like we're decreasing as we go through it if it were the negative sign. It's not. I'm just trying to make the same comparison as we did with the cosines out there. I kind of think that this is all we really needed to identify here. There's no other adjustments, right? So I'm just going to say our function is the sine. And so all that tells me is I know that we're going to start at the center right there. We're going to start at the midline like our sine function does. I know that we're going to increase till we hit our maximum, then decrease. I know that our period is still 2 pi, so I know things like 2 pi units later, that's how long it's going to take for me to get back to my same location and repeat everything out there, right? Okay, sorry, that's a slight lie right there. I know that's where we're going to repeat everything, but I also know that sine of 0 is 0, sine of pi is 0. Sine of 2 pi is where we actually get back to re-experiencing all the same values in the same order again. So this guy is also going to have a sine of pi. Notice if we plug in sine of pi, it's going to give me 0 here, plus 3 will still give me that same height of 3. So I think I can go ahead and then kind of confirm things like halfway in between these two dots is where we get to the maximum. Halfway in between these two is where we get to our minimum right there, because I know that our sine function increases from its sort of starting spot right there. And now I want to stop drawing straight lines like I was doing and draw some actual sinusoidal looking curve. Oh my gosh. Oh my, let's just try the whole thing again. That was not what I wanted to draw. So this thing should be growing and then slowing down, and then there we go. Maybe this is a little bit better. Oop, but it's not. No, okay, that's pretty close right there. And coming back this way, we're getting the same type of stuff right here. Let's see, it should be 4 blocks between, so out to here. So this guy should have gotten down here at negative pi halves down to its minimum and back up again. Notice here things like at negative pi halves, maybe I'll just do a little bit of math right here. 5 sine negative pi halves plus 3. I know that negative pi halves is right down here. It's rotating down the sort of the backwards direction by pi halves to get to the bottom. We ask, what's the sine of negative pi halves? Well, how much vertical action do we have? It's all vertical, so we're going down by 1 unit. So that's 5 times negative 1 plus 3. And that's negative 5 plus 3. And that's negative 2. It's exactly the height that we got to at negative pi halves right there, right? So recognize that we can still do some just plugging in some values, getting out some points right there, as long as we can evaluate our trig function, stuff like that. Let's do one more. It involves a phase shift right here, and then we'll look at our slightly more exciting ones here. So the only modifications I'm seeing here, now that we're getting better at this, is it looks like our midline is at y equals 1, and our phase shift is right by pi sixths. Fortunately for me, I marked off some pi sixths here. By the way, notice our amplitude is still 1 as well. So it looks like my midline is going to be this guy right here at a height of y equals 1. So I'm going to go 1 above it and 1 below it. So going down by 1 just sets me right on the x-axis. Going up by 1 sets me at y equals 2. So I'm drawing my bounding lines for my function. When I draw these, I feel like what this looks like to me is, and maybe, gosh, I don't even know if you guys have this experience anymore. When I was in like 3rd grade or 2nd grade or whenever you learn cursive, you like get your lined paper so that it's got like your lowercase letters should gap here to here. And then if it's a tall letter or a capital letter, it should like span. I feel like that's what I'm doing right here. I'm giving myself like my guiding lines to help me, except those lines on paper are for children, whereas these are for responsible mathematicians, not children. So you should draw those dashed lines, help yourself out with this stuff right here. All right. Now, what I know is that I'm graphing this sine x function, right? And I know that this is the function that passes through the origin and increases as it passes through the origin before it starts doing its wobbling. The thing that we know, though, is that we're going to shift this whole dang graph to the right by pi sixths units. So without a shift, this is where I'd be starting my graph, centered at the midline at x equals 0. But it seems now like we want to shift to the right by pi 6. That's pi 6. So this is the new like dead center of my graph right there. Right? I know that I want to traverse a full, I still have a full period of 2 pi. We didn't adjust the period with any multiple on the x right there. So it's still going to take me 2 pi to repeat again. So that's up to the 13 pi sixths. But as we saw with the previous one, we're also going to get our sine being 0, right? Sine is 0 at 0, sine is 0 at pi, 2 pi, 3 pi, 4 pi. Those are all the places where sine has a value of 0. If this sine function has a value of 0, when you add 1, you do end up at a height of 1. So I'm also going to subtract off pi, and that would bring me back over here. Now I think I kind of honestly have enough to go ahead and graph this guy. I'm seeing 1, 2, 3, 4, 5, 6 chunks in here, so it should be the case that we're going up to our maximum, down to our minimum, halfway in between each one of them, nice and easy. I think I got myself a graph right here, right? So, oops. So I think if we can go do things like confirm that we want to be at negative pi thirds is the x value at which we reach our minimum value in Desmos, then I'll be pretty happy with our like that's kind of a 1 point verification that couldn't possibly be right if we did something wrong out there, right? So let's go ahead and check out sine of x minus pi sixths over 1. Oh wait, plus 1, right? Didn't I just say minus 1? Oh my gosh, what are you doing to me, Desmos? Okay, so I think that's what we had, right? Yeah, plus 1, okay. Cool. And what do we see here? Negative pi thirds, right when we got to that minimum value of negative 1. So I feel pretty good about this graph that we just drew right there. Again, we're noticing that really this is like that point that we wanted to be at right there. What is pi sixths? Or let's just do this. If I do x e... Oh my gosh, come on, Desmos, be my friend today. Okay, and so here where we're seeing this guy is exactly at our, and let me throw on y equals 1 right there as well. And we can see that x equals pi sixth, y equals 1, that is exactly where we're hitting our graph right there at the pi sixth 1. So that was our good sort of, that's sort of our true like starting spot, right? That's sort of like the dead center of this graph has been shifted to the right by pi sixth by that phase shift term right there. So the phase shifts are always a little awkward because they make your graphs no longer centered, and that always makes things a little bit difficult. Again, like turning these off, like our graph is, oh gosh, I'm always trying to click on the wrong screen. Like our graph isn't like nicely centered relative to the y-axis anymore, and that's what makes phase shift difficult to deal with right there. But conceptually, not too bad right there. It's a horizontal shift left or right for our phase shifts. So let's do our very important last component for the class today, which is let's bring this all together now to do a little bit of sinusoidal curve fitting. So we're going to do 2 really good examples right here that are going to show how we can take in data, interpret the data to get a bunch of amplitude, midline, period, phase shift function information, and see if we can predict a function that would be a really good match for that data. Oh, and I forgot, there's one thing I wanted to do that I'm wondering if it works here. It should be the case. Yeah, okay, that's so nice right there. Okay, let me pop back over and show you what we're looking at here. Our first question here is going to be this. Given the following table of values, these are average temperatures in each month of the year in Denver, Colorado. Estimate a possible function to fit this data, then have Desmos do the same and compare. All right, so I'm thinking of this guy right here. I just don't, just let me write. There we go. This is like January, February, etc., right there, right? Month 1, month 2, stuff like that. And this is the average temperature in Denver in that given month, the average temperature over the course of that month. What we're kind of seeing here is we get down to like minimum temperature. Well, let's see. Yeah, it seems like we got down to a minimum temperature in January. It warms up throughout the spring until we reach a maximum temperature in July. This all sounds like stuff I'm expecting to hear. And then it decreases down again to almost the minimum in December. This sounds like exactly like what we think about for monthly temperatures out there, right? What we think is that this should be repeating on a 12-month cycle. So I think that this is something that makes sense for us to do a sinusoidal approximation of, right? Now, the cool thing that you just saw right there, by the way, is that you can literally copy and paste a table like this directly into Desmos, and it will put in a table and plot all of the points. And this doesn't look like some perfect sine or cosine graph to me, but it looks pretty dang close. Close enough that it's reasonable for us to build our own function and to say, here's a very close approximating function to this data. Then we can use the function to make different predictions later. All right. So let's see if we can identify, just using the data, what function we think might be a decent function to describe all this stuff right here. All right. So we want to come up with a trig function that we think is going to fit through this data. Right? So here's the kind of things that I'm observing for myself right here. No? When is it that I'm allowed to write and when am I not? Come on. That looks like it's my min and that looks like it's my max there, right? One of the good things that I'm seeing is that the min and the max are in fact 6 months apart, which is what we should expect. We spend half the year going from bottom to top, half the year going from top to bottom, then repeat. That sounds like a trig function, right? Now, what I know when I come back here to, for example, this graph back here, is I can see my, and let me just get a color here, my min is -2, and my max was 8. My question for you is, how can I convert this min-max information into information I actually want, such as midline and amplitude? Stop and think about it for a second. If you're watching this video later, you should pause right now and figure this out on your own because you can do that. How do I get amplitude and midline information that I want from the minimum and maximum information that in our Denver problem we have? Right? It seems to me like the number that is halfway in between 8 and -2 is the midline, which is 3. If I can then figure out that the midline is 3, it's pretty easy for me to say from the midline we went up 5 and down 5 to get to the min and the max. That's our amplitude right there. So to find our midline, let's find the halfway between points for the min and the max. Once we know the midline, we just got to measure the distance from the midline to either the min or the max, and it should be the same because it should be dead center between them, right? So let's say here our midline halfway between, well, that's just the average. So I'm going to do min plus the max over 2, 29.7 plus 73.5, all divided by 2. I'm going to go to my calculator and get this guy. So 29.7 plus 73.5. I'm going to divide that guy by 2. And I'm getting 51.6. So that seems to me like that should, in a sense, be like our annual average temperature. So I now know that 51.6 is the midline. Now to get our amplitude, should be our distance from the midline to the min or max. I'll do both just to show you it doesn't matter. Oops, I wrote both those words wrong, didn't I? Well, that's not at all what I'm trying to do right there. I'm looking to do our midline minus the min, 51.6 minus 29.7. That tells me we should have an amplitude of 21.9. On the other hand, if we do our maximum minus our midline, then that should be our 73.5 minus the 51.6. And if you do that in your calculator, 73.5 minus 51.6. And oh, what do you know? It's also 21.9. Right? So it looks like we've identified the amplitude of a function that we think we're interested in using, right? So far. Um, so this is a good point where I think it's worth it for us to stop and say, what do we know so far? Don't just try and do this whole thing. I don't know if I want to use a sine or a cosine function, so I'm just going to do my little stupid sine and cosine notation right there. We don't know if we want to adjust the period at all. We don't know if we want there to be any phase shift, but I also do know that we should be adding 51.6 onto the end when we're done, right? That's going to be our midline location there, right? So it looks like what we still have to decide is what's our midline, or sorry, what's our function, what's the period, what's the phase shift. So still three pieces that we need, and then we've got it here, all right? So let's talk about the function. Well, what do we see out here that's going to indicate our function to us? The things that I know, I'm going to scroll up a bit here, is that, and let's look at this graph, for example, I know that the sine function starts at its midline, whereas the cosine function typically starts at its maximum. Our function starts at its minimum. Have we seen a function earlier today that starts at its minimum? Yes. Our negative cosine function starts at its lowest most value because cosine of 0 is 1. So when we negate that, we get negative 1. So things that start at the bottom and then grow are actually kind of some of our really, really typical descriptors here. Whenever we talk about weather over a year, the way that we measure in our hemisphere is from month 1 is our cold one. And so we start at the bottom and we grow up from there, right? In fact, I'd say that the negative cosine function ends up being one that I use kind of the most when I'm building like a real world trig function right here. So I'm going to say, since we start at the minimum, we should use the negative cosine function because it's going to look like this, right? Where we reach that minimum as our starting place. That's January, and then we get warmer until we get to July out here, right? So that says to me, not only do I want the cosine function, I want the negative of the cosine. So I'll also stick a negative in front of the 21.9. The other thing we need to talk about is the period. How often do we think this thing is going to repeat? Well, the period should be straight up 12 because every 12 months, so it repeats every 12 months. So omega is going to be 2 pi over 12, also known as pi over 6. That looks like that's going to be our omega term right there because we're dividing by how long we want that period to be. Multiplying by 2 pi will reduce the period down to 1. Dividing by 12 will re-stretch it back out to being 12 times wider than 1, which is 12 right there. So I've got an omega term. And finally, should there be any phase shift here? This one's sneaky to see, but here's the important thing. When we talk about a function like starting at its minimum, cosine starts at the minimum. When I say starts, what I really mean is the x value is 0 when it gets to the minimum. Do we have x equals 0 for our minimum? No. We actually have x equals 1 for our minimum right here. So it looks like we need to shift all of our x values by 1 to make that happen. So it seems like we need to shift left, or excuse me, shift right by 1. So we should have like a x minus 1 going on here, because now that means, for example, now when I plug in my x value of 1, that's going to be treated like an input of 0 because 1 minus 1 is 0. And that's really what we mean, is that the initial value being 0 is where we get to our minimum down there, right? So it looks like we can now put all this together here. So what did we decide? First thing I have to write is the negative, right? Where we're building off of this thing in the corner up here with all this new information as well. We're going to use the negative cosine function. So negative 21.9 cosine omega should be pi over 6 times x minus 1 plus 51.6. By doing only by hand work, I think that I came up with a good function to model a table of trigonometric data right here. So what we should go do is we should ask Desmos, is this right? And I'm going to do an extra special thing, which is I am also going to ask Desmos to compute its best answer, and let's compare the two. So the two cool things are going to happen here. One, we're going to see, does our curve actually fit through those points? Yes or no? And then we're going to say, Desmos, you fit a curve through those points and tell me what curve you think it should be. That's actually a really special thing that Desmos can do, and we want to see that action there as well. So let's go ahead and do this. So what's my function here? I'm thinking that y equals negative 21.9 cosine of pi over 6 x minus 1 plus, what did we get up? What was our last term over there? 51.6. Oh man. Oh yeah. Oh, I might have to go look at this a little bit later on my own. That's really nice right there. We basically nailed it, right? Obviously, there's a little bit of discrepancy going on out there. That's going to happen with any real world data. The fact that we were able to, by hand, come up with a function that's very closely mimicking this data, that's really cool. And now we can make predictions for any month out in the future as to what we think that temperature is going to be. We now have a function that contains the information associated with that table. That's pretty epic right there. We basically nailed it. I don't think we're going to get much closer than that now. The question that I want to ask Desmos is, hey Desmos, if we couldn't do this, could Desmos guess a function for us based on this table? And Desmos will do this for us. You should notice that we have a y1 and an x1 right here with which to refer to our variables. The ones matter. Down here in my equation, I have y stuff and x stuff. That's a different y and x. This is x1 and y1, and I'm going to use these. So here's the special thing that I'm going to do. I'm going to type in y1, not y. It knows it's a 12-element list. And I'm not going to type equals. I am going to type the tilde sign. That guy right there, it should be to the left of the 1 on your keyboard, right? Up where the numbers are, it's the very upper left corner to the left of the 1. And what I want to do is I'm going to throw in all of these parameters that I want it to solve for. A, cosine, omega, x1, because I'm using the data, minus phi plus k. And look what Desmos did. It created a purple graph that it is claiming is going to be their trigonometric curve of best fit based on some more advanced calculations than we're doing. But look at how dang close we are right here. Like, we also did a very good job. I have a hard time saying that Desmos's graph is significantly better than ours. It's probably a little bit better. If we turn off ours, I think theirs is agreeing with the points slightly better, or rather the points that are above are, in a sense, they're kind of canceled out by some points that are below, stuff like that, whereas ours was like all the points were like a little bit below and there were none that were above, but really, really close right here. So again, you can give a generic formula to Desmos and it will do its best to fit a curve through those things. Which is a super cool thing that Desmos can do. It'll come up with the parameter values. What you can see down here at the bottom is it is proposing what it's believed all of the values should be right there. Notice that we're getting like it was getting 21.1 instead of 21.9 for the amplitude. It was getting a midline of 51.2 instead of 51.6 for the midline. It's getting a little bit more different information here than we were getting for the omega and for the phi. That's a much more phase shift than we were getting right there. A little bit different, but pretty dang close. So super cool. So Desmos you can literally just say, hey Desmos, look, I got this data right here. I think it fits this format of a function. Tell me what the parameters are that make it exactly correct. And Desmos will just do a whole bunch of math underneath the hood to figure out the best possible values for these. And by the way, the last thing is that this number right here being really, really close to 1 means that it's a really, really, really good fit. If this number was 1, then it would be perfectly passing through all the points. So this is a really close fit. So good job, Desmos, but kind of more like good job, us. That's super cool that we're able to do that. I do want to do one more of these because what I don't want to do is lead you to believe that we're always going to get this whole table of data right here all the time. So we're going to look at one more problem before we call it a day that's going to use less information. And here is what I mean by that. You should notice that in the problem that we just did, how much of this data did we really use? We only used the max and the min and kind of some information about X for like our horizontal, like our period and our phase shift. But like as far as Y values go, there were 2 Y values that we basically used to get this. And we didn't really think about what these other ones were going to be. That's probably where the discrepancy is coming up with Desmos, is that Desmos equally used all 12 points information, whereas we were most interested in this min or max right here, just because those are sort of more special locations on the trig function, right? So the question is, well, what if we're really only given just those special Y values? Can we still do this? And the answer is yes, we still can, and Desmos no longer will be able to, right? So let's look at one more right here to see how this is going to pan out, and we'll call it a day after this guy here. So the Old Farmer's Almanac is going to say, in Boston, the summer solstice, June 21st, the day of most sunlight in the year, is going to be, that's the 172nd day of the year. And on that day in Boston, you're going to get 15.283 hours of sunlight. The winter solstice, the fewest number of hours of sunlight per day, you're going to get 9.067 hours of sunlight. And that's on December 21st, which is 10 days away from the end of the year, because that would be December 31st being the final day. And so 365 is our total number of days. So December 21st is 10 days before that, 355 days right there. What I want to know is how many hours of sunlight should we expect on April 1st, if April 1st is the 91st day of the year. So what we're going to do is we're going to build a trig function that should be modeling this number of hours of sunlight. Once we have built our final function, we want to plug in the number 91, and what we're expecting to get out is the number of hours of daylight on April 1st, and it should work for any day of the year, the number of hours of daylight that we can expect, because sunlight does vary sinusoidally over the course of a year, right? So here's what I'm seeing. I'm going to follow kind of our same steps from above. I'm going to say, listen, if we know our min and our max, we can find our midline. If I know my midline, I can find my amplitude. If I know the span of X days that we're looking at, then I can find my period. If I know if we're starting at the min or the max or whatever else, or starting in the middle, I can determine my function. And deciding, did we start at X equals 0 or did we start at some other time? That'll help me determine my phase shift right there, right? So following kind of these same steps right here. So let's do the same first one. Let's do our where's the midline first, all right? What? Can draw, thank you. So midline, average of max and min. Which should be 15.283 plus 9.067 divided by 2. Let me go to my calculator. I'm getting 12.157. Oops, 175. Apparently I'm transposing my numbers in my head here. 12.175. That should be the average number. That should be the number of hours of sunlight during the equinoxes, during the spring and autumn equinox, when there is our middle number of hours of sunlight per day. That's what it should be here. Maybe I'll just identify this. Equinox hours of sunlight. the average over the course of the whole year. So now what I want to see is what's my amplitude? It's my distance from midline to either the min or the max. We showed in the last problem that it's going to be the exact same either way, so I'm not going to do both. I'm just going to do my midline minus my minimum, and that's going to give me 12.175 minus 9.067, and that's going to give me my amplitude of minus 9.067, 3.108. So this should be our number of hours of sunlight gained and lost from equinox to solstice. Boy, I gotta say, sure is nice to have the sunlight that we're finally getting here. Already just in early February, we're seeing quite a lot more sun than we were seeing 6 weeks ago, aren't we? So we got our midline and our amplitude. My next question is, I guess, I don't know, we can follow our kind of same format as we had up here. What should be my period? What should be my phase shift? What should be my function? I kind of think our period is our next easiest one to identify here. Notice that we're defining this by number of days. So since time is measured in days, measured in days, and sunlight amounts, repeat, every 365 days, every 1 year. Our period should be 365, and that says to me that my omega term should be 2 pi over 365. So we're coming up with all these k terms, right? Or all these k terms. That's k right there. We've got k, we've got our amplitude, we've got our omega. We need a phase shift and we need a function. I don't want to talk about phase shift until I know my function though, because that really depends on that. So what I'm thinking to myself here is just like we did with our temperatures here. I mean, obviously temperature and sunlight hours are very closely related. In the winter, we experience our minimum temperatures. In the winter, we experience our minimum numbers of sunlight. So it seems like we're starting near our minimum, but notice that if I'm talking about day x equals 0, that's really sort of like December 31st, right? Day 1 would be January 1st of the year. Day 2 is January 2nd, stuff like that. So it seems like we're going to have some phase shift because our minimum actually occurs 10 days away from that day 0. But I'm thinking of, again, a negative cosine function since we start near the minimum. So again, I'm going to choose the negative cosine function because I'm picturing starting at the bottom and getting more. There's our equinox. There's our summer solstice. Right? Number of hours of sunlight going down and then back up again. I'm going to use this negative cosine of x function. And the final thing I want to think about here is what's my phase shift going to be like? How far off are we from truly starting at the minimum? And I'm kind of thinking to myself here again, I want to kind of identify like what are those days of consideration right there. We should reach And then when's our next one going to be? Well, since our period is 365 days, then the next time that we get back to the minimum should be at x equals 365. We have a min at x equals 355, right? Because we were told that this is the 355th day of the year that we get down to our minimum number of hours of sunlight. So it seems like we are off by 10 days. It seems like we are going to want to add 10 to each of these x values for days so that they correspond to the true minimums that we're going to actually be seeing out here, right? So I think that our final function then will be y equals, so what do we got here? I know that my function is a negative cosine function, so I'm going to stick on the negative. I want my amplitude sitting up front. We got our amplitude of 3.108. That's multiplying by the cosine function. I've got my omega term helping influence my period of 2 pi over 365 times the factored out x plus 10. We need to add 10 to the x values that are being experienced in our problem to make them agree with this trig cosine function right there. And finally, we want this midline of 12.175. So we're adding 12.175. So two things here. One, let's make our prediction. Two, let's verify it in Desmos, and then we will call it a day here. So I'm going to go ahead and come down here. We want to make our prediction. This should be whatever we get from doing 2 pi over 365 times 91 plus 10 plus 12.175. And goodness gracious, I'm going to go to my calculator and I'm going to throw in the whole dang thing here. So I'm going to work from the inside to the outside. The order in which I'm going to do this is 91 plus 10 times 2 pi divided by 365. And that's given me, and I'll just kind of write out a little bit of, right here I'm seeing 1.7386. Now notice that this 2 pi being in here at all was a comparison relative to our radian measurement. So I better make sure I'm in radian mode in my calculator, and I was definitely in degree mode, so I'm glad I checked. Now I'm going to take the cosine of that 1.7386. I'm going to multiply my cosine value by negative 3.108. And I'm going to go ahead and I'm going to add 12.175. And I am getting, check that this agrees with an answer I already had written. That is good. Oops. 12.694. Yeah, April 1. And let's just go to Desmos real quick and verify that this graph looks like we expect it to look. Make sure that this looks like our the correct prediction right there, and then we'll call it a day here. So I just want to throw this function in Desmos here. I'm going to pop back over to Desmos here. So negative 3.108. I'm going to get rid of all this stuff. Turn that off. Turn that off. Y equals negative 3.108 cosine 2 pi over 365 times x plus 10 plus, what was our 12.175? Right. And now, notice that this looks like a flat line. Why does this look like a flat line? Well, the reason is because this is only going out 15 days into the year, and we shouldn't experience a huge change in over 15 days. I know that I need to see this x-axis go from 0 to at least 365 just to see one full period here. So I'm thinking it is worth it for us to modify our x-axis only by like a lot. I don't know. I'm just going out some number of days out there. Sure. So here's negative 600 to 600 for my bounds. I'm now seeing a trig function that's a little bit sensible here. Notice a couple things. First things first. One, 10 days prior to x equals 0, right? This is day 355 over here. This day right here, that's our December 21st right there. 10 days before the new year starts with day 0, that 9.067 was our minimum. So that shift was in the correct direction right there. I can also see that this does come back around to being that minimum right there on day 355. So that right there is exactly it. December 10th, or sorry, December 21st, a minimum of 9.067 on the winter solstice right there. So we've got that information, nailed that. We did see that we were told, oh, why is that ever so slightly off right there? It's only 2 point. That's kind of weird right there. We were told on the 172nd day that we would get to 15.283. I wonder why that's off by like a tiny, tiny smidge right there. That's such a tiny amount to be off by considering how close it is, right? I wonder if there's some place that we did do some amount of rounding in here that I didn't include. I don't really think so. Included a whole number of things for all these guys. In any event, that's got to just be I mean, again, that's incredibly, incredibly close to what we're looking at right here. The final thing I want to see is that what do we get going on day x equals 91? By throwing down that graph in Desmos, it makes it really easy for me to check that 12.694. When we did this 1 second ago, we got the 12.694. It's exactly the same value that we got when we did this guy by hand and in the calculator right there, right? So really cool stuff. We can take in a really, really little bit of information, just information about when is the minimum, when is the maximum, and that's enough for us to identify midline, amplitude, period, phase shift, which of our 4 versions of our trig function, right? Sine, cosine, negative cosine, really 4 functions to pick from to build an overall function. And then we can use that function to make predictions about values that we don't know about in between the minimum and the maximum. So this is definitely something I'll be asking you guys to do a little bit of on our upcoming homework right here. And this is one of those things that I feel like seems a little bit tough, but once you're very comfortable with our 4 features and our function selection, each of these parts individually is relatively easy. Phase shift's always a little bit awkward. People often make lots of mistakes with a positive instead of a negative or vice versa. Whatever. You have 2 choices of direction. Try them both and see which one's right. Like a little trial and error is not going to kill you. You've got Desmos. Just think about taking this class 30 years ago when not only was there not Desmos, but there was like the worst ever version of the TI calculator. You have it good. If you're not using Desmos, you're a crazy person. Get into Desmos and have it do a bunch of the hard work and the trial and error stuff for you out there. That's going to be really helpful for you. So that's going to wrap it up here for 6.8. What we're going to talk about in the next video on 6.7 is we're going to look at the graphs of the 4 trig functions that we care slightly less about. So these are all still things that it's meaningful that you're able to identify them, but there's a reason that 2 sections cover 2 functions and 1 section covers 4 functions. And it's because we care about these sine and cosine graphs at least 4 times as much as we care about the tangent, secant, cosecant, and cotangent graphs collectively. So I do care way more about the 6.6 and 6.8 stuff. You are obviously still responsible for 6.7. So we'll talk about all of our slightly stranger graphs of our less used trig functions in our next video. I will see you guys then. Have a good one, everybody.